All right, my friends, good morning to you all. I think we'll spend most of today on the last part of metabolism, so this puts us about a lecture behind, and we'll just adjust in this part of the class and get where we get. Some of you have asked, what am I supposed to get from this part with metabolism and everything? Well, I've told you you need to know structures and enzyme names and mechanisms, but more than that, I want you to see and I want you to know why these reactions work. In other words, I want you to have a sense for the chemical strategy, which we talked about last time with glycolysis and which I'll continue to point out today. So in glycolysis, we ended up with pyruvate, which has this structure. Still 3 carbons, and ultimately we need to convert it into, through multiple steps, to acetyl-CoA. And notice that we're losing a carbon, so we need to make 1 molecule of CO2. And essentially, we need to break this bond between the carbonyl carbon and the alpha carbon. Strategically, that should be difficult. If it were a beta keto acid, that would be easier, right? You've seen decarboxylation reactions like this where you can, under, say, I think, let's see, what was it in the earlier part of the class, in the malonic ester and acetoacetic ester synthesis, we did something like this where CO2 could leave and you could generate an enol, which would then tautomerize to the ketone, right? And the pattern there is beta keto acid. But what we've got here in pyruvate is an alpha keto acid. And notice that if we tried to push arrows in the same way for the alpha keto acid as we did previously for the beta keto acid, we don't end up with anything that's reasonably stable like this enol. We end up with something else entirely. Sorry. Whoops. I mean, that's better, maybe. Nope. So imagine these electrons kicking down. Where would the aldehyde electron, or where would the electrons be in that bond between carbonyl carbon and alpha carbon go? Well, you would make this weird anion, and that's really unstable. So we'll put the big X of doom on that one, because that just can't happen. But so we need a different strategy. And the strategy is going to involve a really interesting cofactor. So what we're going to talk about now is the pyruvate dehydrogenase complex. This is going to involve multiple steps and multiple enzymes. And in the end, we will end up getting rid of this carboxylate group as CO2, and we'll end up oxidizing this sort of ketone to a thioester. Okay, so step 1 is really the oxidation step. We'll call this oxidative decarboxylation of pyruvate. And here are the key players. First, of course, is pyruvate, which you've already seen. Then there's a new molecule which you haven't seen, and this is kind of bizarre. 5-membered ring containing a sulfur. Then, let's see, 1, 2, 3, 4. And you've got a nitrogen, and then this nitrogen is actually from a lysine side chain in an enzyme in the pyruvate dehydrogenase complex. And I don't know which lysine it is or which enzyme in the dehydrogenase complex it is, and that's not important, but you can see the alpha, beta, gamma, delta, epsilon carbons of a lysine side chain, and then you functionalize the amino group of that lysine side chain with this part, which is called lipoate. And this is an important part of the process. This is actually going to do the oxidation reaction. And the key feature of lipoate is this disulfide. Do you remember learning with, when we talked about cysteine residues, how the cysteine thiol can actually be oxidized to a disulfide? And the reason you can tell that that's an oxidation reaction is look at what's missing, right? We have lost 2 hydrogens and we've lost 2 electrons. 2 electrons are still here, still there, but if you're sort of keeping track of what we've lost, it's a hydrogen ion and a hydride ion. And it's not as though hydrogen gas bubbles off completely. In fact, oxidation of disulfides often happens just spontaneously in oxygen, so oxygen's involved in this process. But the disulfide is an oxidized form of the thiol. Okay, so in this process, I'm going to just get rid of that since we've talked about disulfides. We're going to need a cofactor. Oh, I actually do know what the subunit is. It's pyruvate dehydrogenase complex. The subunit is the dehydrogenase portion. And you need a cofactor which is called thiamine pyrophosphate ylide. And you may have heard of thiamine before. I think it's one of the vitamins, but I forget which one. Its structure is sort of complicated, but you can focus. I'm going to draw the whole thing, but you can focus in on the business end of the molecule, which I'll show you. All right, so over here we've got something that looks sort of like a pyrimidine, and that's linked to this strange 5-membered ring containing both a nitrogen and a sulfur. And it's called an ylide because you have a negatively charged carbon. These electrons are in a sp2 orbital adjacent to the nitrogen that has a positive charge on it. So even though this is neutral, you have positive and negative charges on adjacent atoms, and that's what we call an ylide. And then here's the pyrophosphate portion. And I don't know why the pyrophosphate is there other than to perhaps facilitate interactions with the enzyme. But the really important part of the molecule is right here. So that's what we will focus in on. And people, you can abbreviate thiamine pyrophosphate ylide as just TPP if you want. But the mechanism is really important here. When the reaction's done, we will have, let's see, this portion of pyruvate come off as CO2. And then the remaining atoms in pyruvate are going to end up here. Okay, so the remaining atoms of pyruvate end up right here. And the cofactor will be regenerated, so it's a catalyst. And notice what's changed here. We went from having a disulfide to now below having thiols. So that's an oxidation step. Well, it's a reduction step for the thiol, rather. So this disulfide gets reduced to the thiol. But then look at what happens here. You used to have a ketone with a carbon-carbon bond, and now you have a thioester with a carbon-sulfur bond. So the orange portion gets oxidized, the yellow portion gets reduced. Okay? So that looks like magic mystery chemistry at this point. And I realize that's a lot of stuff to draw. Questions so far about what happens? We're going to talk about how it happens, but the what is important. Okay. So what is behind this mystery of an alpha keto acid being able to decarboxylate? All right, let's show you. So if you look at the thiamine pyrophosphate, or TPP, what you see is you've got an aromatic ring. There's a couple of lone pairs on sulfur, but only one of them is involved in aromaticity, 2, 4, 6. So this is an aromatic ring. The nitrogen's positively charged, and then because it's positively charged, you can remove the proton. Well, let me just show you the alternative form of this molecule. Okay, so because this molecule has a positive charge on this nitrogen, it's actually quite easy for a base to remove this proton and give you the thiamine ylide. All right, so here's pyruvate. And then here's that thiamine ylide, which we're just going to abbreviate as follows. Okay, so when we remove this proton, which was lying perpendicular to the plane of the ring, the lone pair that's left behind is in an sp2 orbital where it's nucleophilic. Okay, so these electrons in an sp2 type orbital can attack the ketone. And that seems reasonable. A negatively charged carbon should be a good enough nucleophile to attack the carbonyl carbon of a ketone. If we wanted to, we could show electrons going straight up to that oxygen to give you a tetrahedral intermediate, which we would then protonate on the oxygen, though we'll combine that with the proton transfer step just to make our lives a little bit easier. All right, so what should we have when a nucleophile attacks a ketone? Well, you've made a new bond between the carbonyl carbon and the nucleophile, and then your oxygen on your ketone becomes an OH group. This should be really, really similar to stuff you saw early on in carbonyl chemistry. This would be like reducing a ketone to a secondary alcohol or reacting a ketone with a Grignard reagent. Okay, so we have this secondary alcohol. I'm now going to redraw it in a way that I think will help you see, will help you see where the decarboxylation reaction is going to happen. But before I do that, any questions about that first step? You know, if you're trying to categorize these reactions in terms of things you've seen before, this is nucleophilic addition to a ketone. All right, so I'm going to redraw this molecule. Here is the acid group. Now go and convince yourself that I haven't done anything illegal or untoward. Okay, do you see here's the carboxylate group. Carbonyl carbon, alpha carbon. We could even now call this carbon from thiamine the beta carbon. Okay, what similarities do you see between what I've drawn above and a beta keto acid? Quite a bit of differences, but are there any structural similarities? You got nothing? It's okay. Look at the beta carbon in a beta keto acid. How many bonds to a heteroatom do I have on the beta carbon? 2, right? Up here, how many bonds do I have? Also 2. So when we have thiamine attack the ketone, we turn what was an alpha keto acid into something that looks a whole lot like a beta keto acid. The difference is that whereas we have a ketone here, we've got this iminium ion here. Now, watch what can happen. Do you remember that when we do a decarboxylation reaction, we form an enol, and we get this kind of intermediate. And if there were some R group on the alpha carbon, it would end up there. Let's see whether we can do something similar with this carboxylate once we make this intermediate. So electrons kick down, and then just as we did for the beta keto acid, we're going to have electrons from the bond between carbonyl carbon and alpha carbon move over here to make a new pi bond between alpha and beta, and then we have to move these electrons up onto the nitrogen. The only difference here is we don't need to pick up a proton to get a neutral intermediate because that nitrogen's already positively charged. So all right, So let's draw what would happen after we do that. The molecule that's left looks like this. Okay. So do you see this sort of analogous to the enol form? Here's the double bond, and then here's that nitrogen that was part of the iminium ion. And do you see how we've lost CO2? Okay. This molecule has a resonance structure. We can draw it like this. And in that resonance structure, you have a lone pair on what used to be the ketone carbon. Okay, so again, I want you to notice the unusualness of this chemistry. The ketone was at the alpha carbon. We've gotten rid of CO2, so now we've just got this alpha carbon. Here was our carbonyl carbon. Here's now the alpha carbon. And the alpha carbon is nucleophilic. Maybe I didn't explain that well enough. Actually, that's kind of silly. I'm sorry. Typically, when we deal with carbonyl compounds, they're nucleophilic at the alpha carbon, where you make an enolate, right? But we almost never see carbonyl carbons that are nucleophilic at the carbon, right? We've never done anything like that before. But because of thiamine, we've turned what used to be a carbonyl carbon into something that's alpha to another carbonyl. And that allows us to basically be nucleophilic on what used to be the carbonyl carbon, and it's going to react kind of like this. Okay? That concept of being nucleophilic on an atom that isn't usually nucleophilic has a name in organic chemistry. It's German. It's Umpelung, which I think means opposite of what you would expect. If I'm wrong on that, I'm sorry, but they do use the word Umpelung. So, question on the final exam. What is Umpelung, right? Let's scare the people at home by me not actually saying that I'm not going to ask that on the exam. Whoops. All right. So what's going to happen now is this molecule that's nucleophilic on what used to be the ketone carbonyl carbon, that's going to attack the disulfide of the lipoate group. Okay, remember that's up here. I showed you this is an extended arm, a modified side chain in the protein, and that's held in the active site. And so what we will show is this negatively charged nucleophilic carbon attacking the disulfide, and it actually there's evidence that it attacks the internal one here. I don't really think that detail's that important. And we pick up a proton on the other sulfur. And the intermediate that we form when we do that looks like this. Still got a positive charge on the nitrogen. And I guess we can draw that. All right. So then at this stage, we're going to have a base, remove this proton, electrons will kick down, and the thiamine ylide will leave as a leaving group. It attacked as a nucleophile. At the end, it's a cofactor, so it's going to be regenerated. The pKa of its conjugate acid is such that it's an OK leaving group. And then look at what's left. We now have an acetyl thioester. Where the two carbons from pyruvate that are there end up here. Okay? Questions you want to ask about that step? We use the thiamine ylide as a nucleophile to convert an alpha keto acid into something that looks more like a beta keto acid, which can decarboxylate. So right here is our first loss of CO2. So the stuff you're breathing out, one of those comes, some of that comes from this step. And then after the decarboxylation, we have the carbon that was alpha to the carboxylate and alpha to the iminium act as a nucleophile to attack the sulfur disulfide bond, break that bond, and make a new carbon-sulfur bond. And then when we kick thiamine back off as a leaving group, we've now got a thioester. So the key reduction step of the thiol was right here when we broke the sulfur-sulfur bond and replaced it with a carbon-sulfur bond and a sulfur-hydrogen bond. The key oxidation step was here where we made a new carbon-sulfur bond. All right, so that's our thioester. What else? Man, we keep this up, we're going to need a whole other day on metabolism. But whatever. Okay, so the next step is sort of boring in contrast to the other steps that we've talked about, which are slightly less boring. This step we're going to call Transthio esterification. And all that's going to happen here is that we're going to take our acetyl thioester that's attached to the enzyme via this lipoate group. And we're going to add acetyl-CoA, the coenzyme A thiol, which I still haven't drawn for you, and maybe won't. And the products are going to be the CoA thioester And then you're simply going to release the other thiol. So and the mechanism of this reaction is nucleophilic acyl substitution. So if I asked you to draw a mechanism of that, you should be able to do so. You would need a base to remove a proton from the sulfur, then have the negatively charged thiolate attack the carbonyl carbon to get a tetrahedral intermediate, then kick off the other thiol. So a very, very simple nucleophilic substitution reaction at a carbonyl carbon. All right. The enzyme that does this is called dihydrolipoyl transacetylase. The dihydrolipoyl stands for this group, the lipoate that we have reduced. The dihydro tells you that it's reduced. And then the name transacetylase tells you that you're moving the acetyl group from the thiol of the lipoyl group to the coenzyme A. All right. So I don't think we need to spend too much time on that. The final step is pretty complicated, and so we're not going to worry about the mechanism of this. Basically, you're going to take the dihydrolipoyl group and oxidize it back to the disulfide so that you can do the reaction again. And the mechanism involves FAD as a cofactor, NAD plus as an oxidant, and the enzyme is called dihydrolipoyl dehydrogenase. After the reaction's done, we will have regenerated the disulfide bond. Notice that that's going to require loss of a proton and a hydride, and we will generate an equivalent of NADH through that process. Okay, so the mechanism is complicated. It involves a couple of different disulfides in the dehydrogenase molecule. If you want to see it, you can come up to my office and I can show it to you, but I think it's simple enough to recognize that it's an oxidation reaction where we lose a proton and we lose a hydride. And that hydride ends up on NADH. And then the proton ends up attached to some base. Okay? So we lose the yellow proton and the red hydride, and that's an oxidation reaction. And that regenerates our disulfide. Okay. So at that point, we are ready for the amazing citric acid cycle. So you want to take a breath and sort of stretch mentally for a moment. To review where we've been, remember fatty acid metabolism led us to acetyl-CoA. We talked about how amino acid metabolism led to acetyl-CoA, though we didn't show any examples of that. Now carbohydrate metabolism is leading to acetyl-CoA. Now, you were told long ago that glucose gets oxidized to 6 molecules of CO2. Remember, 1 molecule of glucose produces 2 molecules of pyruvate, so we have lost 2 of our 6 molecules of CO2 so far. Now we have to find a way to convert this ketone into a carboxylic acid, have it pop off, and then we have to find a way to convert this methyl group into a CO2 group and have it disappear. That chemistry is complicated. There's no way to do it directly. So what we're going to do in the citric acid cycle is we're going to incorporate acetyl-CoA into an existing host molecule, and then we're going to do all sorts of things to rearrange the structure of that host molecule such that we can do decarboxylations. All right. So in the citric acid cycle, this occurs in mitochondria, unlike glycolysis. And this is something that the citric acid cycle is present in mitochondria in eukaryotic cells. Bacteria don't have this. And the citric acid cycle facilitates what's called aerobic respiration because the NADH molecules that we make from this process are going to go to the electron transport chain where they'll donate electrons to reduce oxygen. That drives a proton gradient and then allows for ATP synthesis. So in the citric acid cycle, we will take 2 molecules of acetyl-CoA, 6 molecules of NAD+, overall, let's see, 2 of FAD, 2 of GDP, plus 2 of phosphate ion, plus 6 H2O. And in the end, we're going to get 2 molecules of CO2. Coenzyme A will be released. I guess we get 2 of those. We'll get 6 NADHs, 2 FADH2, 2 GTP, and a couple of protons. Sorry, it's 6. Sorry. All right. And then each NADH can go to the electron transport chain and is worth around 3 ATP per NADH. And each FADH2 can intercept the electron transport chain a little bit downstream because of its lower reduction potential. That's about 2 ATP per FADH2. So overall, if you do the maths, you're going to get about 24 ATP out of this process. And if you think about what we did in glycolysis, what was it? The yield was maybe 2 measly molecules of ATP and a couple of NADHs or something like that. So this is where most of our energy comes from. All right. So couple of things about the citric acid cycle. Because it is a cycle, you could think about it entering it at any, well, we'll start at the step where acetyl-CoA gets incorporated. You're going to find out really quickly that we're going to lose track of which carbons are our original acetyl-CoA carbons, and it's not going to matter. Eventually, as the citric acid cycle turns, we will get rid of 2 molecules of CO2. The weird thing is that if you try to follow an individual carbon from acetyl-CoA through the citric acid cycle, it might need to go through a couple of times before that carbon gets a chance to leave as CO2. We're not going to go through it at that level of detail. I've tried it before, and it sort of drove me a little bit crazy. And one of the intermediates is symmetric anyway, so at that point we lose total track of where the carbons are. But just understand that we're not actually going to see this carbon, the methyl group, oxidized. We're going to see that incorporated, and then we're going to make changes to the molecule, and eventually we'll lose 2 CO2 molecules. All right. So here we go. Acetyl-CoA enters the citric acid cycle with a host molecule called oxaloacetate. And this is a 1, 2, 3, 4 carbon. Shoot. What am I doing wrong here? Oh. Sorry, it doesn't matter, but I'm trying to draw it in my notes so I get, like I did in my notes, so I get the right number of carbons. Okay, this is oxaloacetate. It is an alpha keto acid, and it's also a beta keto acid. So it's interesting that we've got that structure. We know interesting things to do with alpha keto acids now because of TPP. We also know interesting things to do with beta keto acids. This is, of course, acetyl-CoA. The enzyme that catalyzes this process is called citrate synthase. And when we're done, we're going to get, as a product, okay, so this is citrate, and we're also going to get coenzyme A off as part of this process. The mechanism is basically going to be aldol reaction followed by thioester hydrolysis. Now notice that here are our 4 carbons from oxaloacetate, and you can think of those as ending up there. And then here are our 2 carbons from acetyl-CoA, and you can think of those as ending up there. Okay? However, comma, we don't usually pronounce commas, sorry. Notice that citrate is achiral. It is an achiral molecule because this arm of citrate is identical to that arm of citrate. You see it? This carbon here is not a stereocenter. So at this point, we lose total track of where the acetyl-CoA carbons are. We don't know, which is great. And from this point on, we're just going to not worry about it. So you could also, what I'm trying to tell you is that you could also make the case that no, it's this one that's oxaloacetate and this one that's acetyl-CoA. Difficult to say, and either one is fine. All right. So what would the Aldol mechanism look like? Well, what does the Aldol mechanism ever look like? First, a base would remove a proton from the alpha carbon of acetyl-CoA to give you an enolate. Now, if it's all right with you, I would like to, instead of showing that enolate intermediate, I would like to just show this directly attacking, not that one, but the ketone. Can you tolerate that? Can you understand that as we make an enolate first and then we attack the ketone? And then at the same time, we could show a tetrahedral intermediate like this, but let's make our lives easier and just show the negatively charged oxygen on the resulting alcohol picking up a proton. So basically what we've done here is shorthand for make enolate, attack the carbonyl carbon, and protonate the negatively charged oxygen in the tetrahedral intermediate. And previously we would have drawn that out in 3 different steps. Here, because I am lazy, we are doing it this way. If you want to draw them out individually, that's fine too. I promise not to put this on the exam and ask you as a trick question, is it reasonable or not? And then say, no, it's not reasonable because they don't actually all happen at the same time. That would be wrong. Okay. It would also be wrong to assume that they do happen at the same time, but we're just doing this as shorthand for this process. All right, so if we do that, the product of that step is the same as you would expect for an aldol reaction. Oops. And so here's the carbons from oxaloacetate, as far as we know. Here used to be the carbonyl carbon of the ketone. That's the one that got attacked. Here is the new bond we made. And then here are the two carbons of acetyl-CoA. And notice that this follows the familiar pattern of aldol products. Carbonyl carbon of your enolate nucleophile, alpha carbon, and then beta carbon. The product here is a beta hydroxy carbonyl compound. So that's how you can tell that this was an aldol reaction. Okay? Questions so far? Okay. Then here, I'm not going to show this process. This is just another example of nucleophilic acyl substitution, where we're going to remove a proton from water to get hydroxide. Hydroxide will attack the thioester to get a tetrahedral intermediate. The thiolate's a better leaving group than hydroxide, and so the thiolate gets kicked off. We make an acid, and it loses its proton at physiological pH. See if you can envision that in your head, but this kind of ester hydrolysis is exactly the same kind of thing we've been doing since the first exam. All right, so now we've, and by the way, thioester hydrolysis is downhill in energy, which provides some of the driving force for this process to occur. All right, so our goal in the citric acid cycle, now that we've committed and incorporated acetyl-CoA, our goal is going to be to lose 2 molecules of CO2, either from a beta keto acid or from an alpha keto acid using TPP. And our second goal is going to be to regenerate the oxaloacetate starting material. So the first few steps are all about getting rid of CO2, and the second steps are about regenerating oxaloacetate. Okay. You sick of this? Pretty sick of this? Okay. Well, as long as you promise not to make a big deal on the student ratings of ends class starts and ends class on time, you can just, actually, you can do whatever you want on the student ratings. By the way, the university does rely heavily on student ratings. I read them every semester in an attempt to improve what I do. Your feedback is really appreciated, so make sure you fill those out. I will see you next time.